Good afternoon, this is Schweitzer, and quick little answer key for a workbook page. Few things here that you might want to note is this first section here is just review from from the previous concept. So again, quickly through that. Suppose you throw a tennis ball up in the air. What does the kinetic energy of the ball increase, decrease, or remain the same? Well, okay, so we have a ball. It's throwing up fast. It's very fast at the bottom, and then at the top, it's very slow, or it might even it's going to stop eventually. So that means the kinetic energy is going down, but the potential energy is going up. So the answer is it goes down, and it's converted from kinetic energy is converted into potential energy. This goes down, this goes up. Okay, what is a calorie? It is energy. And needed to convert to raise 1 gram of H2O to from all right, raise 1 gram of H2O 1 degree Celsius. So raise 1 gram of water 1 degree Celsius. Okay, this guy here is just going to be times 1,000, which is going to be 255,000 calories. This guy from this here to kilojoules is going to be 232 calories. Get rid of calories. Get rid of calories and go to joules, and then get rid of joules and go to kilojoules. This is 1 to 1,000. This is 1 to 4.18. This is 1 to 1,000 equals. All right, grab your calculator here. The thousands will cancel, so it's really just going to be 232 times 4.18, and there we go, 969. All right, 969 joules. All right, 10 gram block of aluminum increases 10 degrees Celsius. How much energy to gain? All right, to solve this problem, you need to go and figure out what is the specific heat of aluminum. This is going to be in your workbook, or there's a chart for it, but it is 0.9 joules per gram per degree Celsius. And that is important to know that number, but it's really important to understand these units. That's the energy that's to raise 1 gram of aluminum, 1 degree Celsius, 0.9 joules. So this we call the specific heat. Now, on this guy, you might note that that's awfully similar to this guy. This guy also, this also is considered the specific heat of water. All right, this is 4.18 joules per gram per degree Celsius. Okay, so a 10 gram block of aluminum increases 10 degrees Celsius. How much energy to gain? All right, so we could use this formula, which is just going to be, and you could also use these units to just factor label it, but it's going to be the energy equals the mass times change in temperature times specific heat. So we're looking for energy, which is Q. The mass is 10 grams. And if you forget the unit that this thing is, look over here. It's on here. It's grams, Celsius, joules. Joules, grams, Celsius or Kelvin, and specific heat. All right, this guy is 10. This guy is 0.9. And away we go. This is pretty easy. So 10 times 100. 100 times 0.9 is just 90. All right, 10-gram block of copper has gained some energy, as in the previous problem. Well, the same energy, so 90 joules. So do that here. So this guy, again, we need the specific heat of copper, and the specific heat of copper is 0.36 joules per gram degree Celsius. So notice that this is almost a third of it. So it takes less energy to raise it up a degree Celsius. All right, so copper will be this guy. Q equals mass times change in temperature times specific heat. So Q is going to be what we're looking for. Oh, no, Q is 90 joules. The mass is 10. The specific heat is 0.36 times the, let's back that up a second. Okay, the Q is mass, so the Q is 90. Mass is 10. Change in temperature is what I'm looking for here. And then the specific heat is 0.36. And therefore, solve all for delta T. Now, delta T is not, we don't know the initial temperature, so I can't give the actual final temperature. But I do know it should raise up more than 10, in fact, almost 3 times 10. So 90 divided by 10 divided by 0.36 equals 25. Okay, so this equals 25. You're saying it's not 3 times 10, but it would be if this was 0.3. Exactly 1/3. All right, so 10 grams of ice gain the same energy as the previous problem. What will it change in temperature? Okay. Now the specific heat of ice is not the same as normal specific heat of water. You want to look on your laminated sheet. Actually, not laminated sheet, but it's on your book chart, and I'll add it in here. I'm not gonna. I don't know it offhand, so it's like, well, normal specific heat is like 4.18, but I think it's like 2.4. But I'm not going to put this on here. I'll just put down the work for it. Q equals the mass times change in temperature times the heat. So we'll put the 90 in here. You're going to put the 10 in here. Okay, change in temperature is what we're looking for. This guy right here. And then heat is unknown. I gotta look that up. That you need that guy right there. Okay, so look this up. It's the same problem, but so. All right, a 10-gram sample of water contains 25 degrees Celsius. And again, we could do this the previous problem, but it says ice. And ice has got a difference between heat than even water. 10-gram sample of water at 20 Celsius gains 25 joules of energy. What's the final temperature? Okay, so let's do this. So we're going to use this guy here. Q equals mass times change in temperature times specific heat. So Q is going to be the 25 joules. 25 joules. The mass is 10 grams. Change in temperature is what they want. They want TF. Okay, so there's a couple things. You could go TF minus, and then you could go like this and go 25. 25, of course, now if you do it this way, you have to make this 298 Kelvin. 298. And then times heat of water is 4.18. Now to solve this is just a little bit more difficult. Now the way I would do this is I'd multiply, times each other here, and then I distribute, and then I would divide out and get the TFs on one side, non-TFs on the other, and then I would just solve it out. So this is going to give us, and we'll do this quickly here. That's what 40. So it's going to be TF minus 298 times 40.18. Distribute is going to give us 40.18 TF minus, and you're going to multiply that 298 times 40.18, and then we're going to get 11,973. 11,973 equals 25. So now I just add over this side here plus 11,973, divide out the 40, and finally do that. So plus 25 gives me 11,998, and divide that by 40.18, and we get 298. All right. All right, so do the math quickly here. Alright, so we have a TF here. I'm getting 298 here, but I know that's wrong, and I'm not going to redo the video. So we'll put this here, and we'll solve it out the other way. Making some clerical mistake here. We'll find it out in a moment here. So that's a little bit longer way. The easier way is going to be just solving it for this guy. So I have 25 equals, okay, 10 times delta T, and then times, and then we have, okay, I'm looking for specific heat of water, 4.18. And then the math, just multiply those two, divide out. You don't need to be in joules or, well, here we do it here. So 25 divided by 10 divided by 4.18, and we're getting 0.5. I see that's maybe, well, I don't know, 0.59 is the answer. So delta T, oh, it was the right answer. Okay. All right. So the answer is really, it's not changing much. 0.59, 0.59. So this answer was 298.5. All right. That's where, for some reason, I was just seeing that wrong. So it was like, I was getting confused because this is the same as we started with, and the answer is yes. It's like 25.5, So, so this is my change in temperature. So you would need to take the delta T, take your delta T right there, and then you'd have to take 25 degrees Celsius, and you'd have to raise it up by that amount. Okay. What can you say about the heat of water or substance? Well, this is very large. It's unusually large. It's like biblically large. It's so unusually large. It really makes Earth what it is. If water didn't have this super, super, super high heat, our life here would be much different. The speed of the sample of water gained by 10 kilocalories of energy, causing the temperature of water to change from 25 to 30. What's the mass of the water? Okay, so again, Q equals mass times change in temperature times specific heat. Okay, so my energy is 10 kilocalories, so that's 10,000 calories, which times 4.18 is 41,800 calories. 41,000, yeah, 800. All right, and then equals the mass, a sample of water gained. Okay, we're looking for the mass, and that's that. Change in temperature is only 5 degrees. All right, and then 4.18. So really, this is just an exercise in a little bit of algebra. So we have the original 10 times 1,000 equal 10,000 times 4.18 is 41,800 divided by 5 divided by 4.18 is 2,000. All right, so at that point, the mass equals 2,000, and the unit would be in grams. All right. 150 gram sample of an unusual substance absorbs 3,000 joules of energy and only changes 4 degrees. What's specific heat? That's a lot of energy for such a small degree change. So we have a very large specific heat. All right, so 3,000 joules equals 150 times specific heat times 2. All right. So we got 3,000 divided by 150 divided by 2 equals 10. All right, so this heat equals 10 joules per gram per degrees Celsius. Occasionally, you'll see this listed as Kelvin, and that's fine. It's no difference. A 100-gram aluminum block, mass 50, is dropped in 100 grams of water. The block drops 29 degrees Celsius. How much energy did the block lose? How much energy did the water gain? So we have a situation where we have a sample of water, and the block is dropped into this guy, and it radiates energy out. So all energy lost by the block is gained by the water, so it's the same number. All you gotta do is this, go 100. So it's going to be Q equals mass times change in temperature times the heat. Okay, so we're looking for Q equals the mass. Let's just see how much does the water gain. Okay, so drop 100 grams of water, the block drops 29 Celsius. Okay, so I'm going to calculate out, well, there's two ways you could do this problem. Since we know that it's aluminum, let's go with it this way. 0.9 is the specific heat. So this is 0.9. And this guy change temperature is going to be 100 minus 29. And we're looking at, what is 71. Okay. So this is going to be 71 degrees. And the temperature, the mass is what we're, okay. So aluminum block mass of 250. Okay, and we solve for Q. All right, so 250 times 71 times 0.9 equals 15,975. So we have 15,000 975. Now this is with the aluminum version. You could do it also with the water. If you have all the data for the water, and so the water, it says 100 gram, it's dropped in 100 grams of water. Okay, we don't know the starting temperature of the water, so we can't do that. Okay, all right, we'll leave it at that. This is our answer located here in joules. And there we go. Thank you very much.